Okay, so here we are with graphing other trig functions, and by other we mean tangent, cotangent, secant, cosecant. Now, this is a topic that we're not probably going to test you on or expect you to be able to perform. However, it is a topic that we'd like you to know about. So we're going to go through at least the notes with this, and then we'll probably just continue to graph sine and cosine as our practice. But otherwise, let's first take a look here at tangent. So the graph of tangent is going to be one full cycle from 0 to pi, okay, because tangent will repeat after pi radians. So the period for tangent will not be 2 pi, it will be pi. The one thing we need to be concerned about, though, is that there will be a vertical asymptote, okay, at pi over 2. Now, the question is, why is that? Well, at pi over 2, think about your unit circle, okay? At pi over 2, the coordinate is 0, 1. Okay, so tangent is defined as y over x. So by definition, that means the tangent of pi over 2, or 90 degrees, okay, equals 1 divided by 0. And we know that we cannot divide by 0. So that's why that vertical asymptote appears. It would have been like graphing rational equations or rational functions when you were in algebra 2. Anytime you had an x in the denominator, you were not able to graph that. So what we'll do here is we'll go ahead and first put in our asymptotes every pi over 2. Okay, so every time we're at pi over 2, so that's 3 pi over 2 as well. Okay, negative pi over 2, negative 3 pi over 2. Okay, now there's not a necessarily a 5-point graphing method here for tangent, but there are a few important points that we should know about, okay, that make it a little bit easier to graph. First of all are the zeros, right? So on back to that unit circle, every time that x is 0, okay, or excuse me, that y is 0, okay, that means we'll be doing 0 divided by 1, which is always 0, okay? So y is going to be 0 at 0, pi, 2 pi, 3 pi, so forth. So we're going to come over here and put our zeros on. All right, so 1 divided by 0, or excuse me, 0 divided by 1, 0 divided by 1, 0 divided by 1, same over here, same over here. Okay, now the other points that we could probably plot here are our 45-degree angles, right? Because at those 45s here, so pi over 4, 3 pi over 4, etc., okay, they're isosceles triangles, which means we have root 2 over 2 divided by root 2 over 2. Anytime you take something divided by itself, you always get 1. Okay, so over here, you know, at this one, we would have positive 1 because root 2 over 2, and then here, negative direction, we'd have negative 1 because one of those will be negative. All right, same thing here and here, okay. The other one's off the grid, same thing here and here, and it still follows the same sort of pattern. Now, the tricky part here is what happens as you approach this asymptote. Conceptually, this is going to be a little bit difficult for us to understand, okay, but what we're looking at here is as you approach the 90 degree, right, on the unit circle. So we're la-di-da-di-da, coming around here, okay, we're getting really close to that 90 degree, which means that our x value is getting really close to 0, okay? So our x value is decreasing, okay? Our y value is increasing, getting closer to 1, all right? But that x value is the important one. We're dividing by a number that's getting closer and closer to 0. So we're dividing by a number that's really small. So let's take it to an extreme. Let's take any y number, doesn't matter what it is. Okay, so like if we just use 1 as our point of reference, let's say we're almost at 1 but not quite there, and we divide by a really small x number. So instead of 0, because we know that'll be undefined, let's divide by 0.1. Okay, and if I take 1 divided by 0.1, I'm gonna get 10. All right, but then let's take it further. Let's get closer to 0. Let's divide by 0.01. So 1 divided by 0.01 is going to be 100. Ooh, that's getting really big, right? So the result keeps getting bigger. I bet you can't guess what 1 divided by 0.001 is, right? 1,000. Okay, so as we get closer to that place on the graph, right, that's undefined, our results are getting really, really big, right? So that means that as I approach that asymptote, okay, my curve is going to infinity. Okay, same thing here. As I approach the asymptote this direction, my curve is going to negative infinity. All right, same concept. So that's why that happens. Anytime you take a number, okay, divided by a really small number that's close to 0 but not 0, okay, so 0.0000 number, okay, we're going to get infinity. All right. So that pattern just repeats itself because it is periodic. All right, for tangent. Okay. And if that one-time explanation wasn't enough, I can certainly explain it to you in class as well. Okay, so that's what tangent looks like. All right, so again, domain, all real numbers, all right, that are not equal to pi over 2n, okay, would be what we're looking at there, where n is an odd integer. Okay, so that would be, 1 pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, and so forth. Okay, the range here is going to be all real numbers. All right, x-intercepts are every pi. Okay, so pi n, and n's an integer there. There is only one y-intercept, and that was at the very beginning, the origin. Okay. And those asymptotes are also going to be at the same place where the domain restriction is. So again, pi over 2 n, and n is an odd integer. Now you can shift and so forth with tangent the same way you do with sine and cosine. Obviously, it's a little more difficult to think about. So we're not going to expect that from you. We just want you to know what it looks like. All right, now cotangent. The only difference here with cotangent is that we're flip-flopping the x and the y, which means the asymptotes are going to appear at different places, right? So instead of those asymptotes being at pi over 2, okay, for cotangent, we're dividing by the y value, so it's where y is 0. So we're going to be at 0, pi, 2 pi, so forth. Okay, but the curve itself still stays the same, all right, because we're still dividing by the same two numbers, just in a different order. Okay, so now our vertical asymptotes are every pi. All right. And then we are okay. And then for that one there, we are going to be getting our 0 value at pi over 2, right? Because now it's cotangent obviously is x divided by y. So where x is 0 is where those zeros are going to be. So here, 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 and here. Okay. And same idea, it's still going to equal 1 at the same places, right? So those values aren't going to change. All right, so they still equal 1, okay, here and here, because 45, it doesn't matter if it's one number divided by the other or vice versa, right? It's still going to be, all right. So it's going to look something like this. So much of the same from cotangent as tangent. Okay. And again, we're just looking at the sketch for now. All right, we don't need you to be able to shift it or so on and so forth. Okay, just this is what the graph of cotangent would look like. Again, the Desmos app is a great way to graph tangent and cotangent. It will give you all of this information. So if I jump out there real quick, let's take a look at what it looks like. Okay, so if I say y equals, go to functions, tangent, okay, of x, whoops. All right, you'll see that I get, that funny looking graph that I was just talking about. Okay, so let's change our axes there. Let's go from negative 2 pi, okay, to 2 pi, so we can kind of look at what we were looking at on our screen. Okay, and our step there was pi over 4. Okay. So you'll notice that we get the same looking graph that we had there. Now let me add the asymptotes. So for tangent, we said it was pi over 4, or excuse me, pi over 2. Right? I'll make that a dashed line, so that way we can see that it's an asymptote. Okay. And I would have to add that in for all of them if I wanted to look exactly like the ones that we graphed, but you get the general idea that this is what we're looking at, okay? And you can see where the asymptotes are there, all right? So again, you could use the Desmos app there as a way to look at these as well. Okay, so let's go down here to secant and cosecant, okay? So cosecant is the reciprocal of sine, so it's important for us to remember or recall what sine looks like. So I'm going to go ahead and just graph sine for us, right? 5-point method, so 0, 0 is where it starts. Okay, last point's going to be at 2 pi because we have no transformations or manipulations at this point. Middle point's going to be at 0 as well. And then I have intercept, then I have max, and then I have min. So I give a quick sketch here of my sine curve, okay? And then I'm going to go backwards across the grid the same way. All right, and I have my negative half here of the sine curve. All right, so when I take the reciprocal of this, remember where those issues happen for tangent and cotangent. It'd be a good jumping off point first here. Anytime we have an x-intercept, okay, that means that y value is 0. So if we flip-flop that point, okay, that's going to be bad, right? That's going to be where those asymptotes occur, okay, because we're taking the reciprocal. So remember, like the coordinate here is pi, comma, 0. All right. If I take the reciprocal of that, all right, then I'm going to have 0 in the denominator, which means that I will have an asymptote. All right. Now, just to refresh us where that's coming from, remember that cosecant is the reciprocal of sine. Right, so sine at pi, again, just to rehash this, sine of pi, okay, is going to equal the y value over r, right? So the y value is 0, and the radius of the unit circle is always 1. What we're saying is that when we do the cosecant of pi, that fraction flips, and I have 1 divided by 0, which is undefined. Okay, so that's where that asymptote comes from. All right, now again, I can get into the discussion that we just had with tangent about why this happens, but as I'm on this curve getting closer to 0, okay, as my x values approach that asymptote, that pi value, my y values are getting smaller and smaller and smaller, right? So instead of dividing by 0, right, I'm dividing by a really small number that's close to 0, like 0.0001. Okay, so same discussion as last time. What's 1 divided by 0.001? Right, we get infinity. Okay, so that means that this curve here for the reciprocal is going to look like this. All right, same thing down here, except negative. Now, why do these points stay the same? Okay, is a good question. Well, what's the reciprocal of 1? Still 1. Okay, so those points didn't change. So over here, and up here, and it just continues in that pattern, all right, forever and ever. Okay, so the green graph there is with the asymptotes would be our graph of cosecant. Now, again, I'll jump out here to Desmos. Let's take a look, see if I got it right. I hope so. So y equals the cosecant of x. All right, let me zoom out here just a little bit so I can see negative 2 pi to 2 pi. And you see that we got it right. So every 0 or pi value was where that vertical asymptote was. All right, the curve comes down, touches 1, goes back up. Okay, because again, the reciprocal of 1 is 1. All right, good. And last there, we have the graph of secant, which would be the reciprocal of cosine. Okay, so same idea. I'm going to first give myself a quick look or refresher here on cosine, right? So max, max, middle is min. Okay, intercepts. So much of the same here from what we've been doing. All right, no shifts or transformations, just a straight cosine curve. All right, and then the process is the same. So without getting into a deep discussion about it, those asymptotes are going to happen at the intercepts again, because again, those are the places where we would be dividing by 0 in our definition of secant. Okay, so those are the places where the x value is 0. So every 90 degrees, every pi over 2. Okay, and then the curve itself is, like we talked about, that weird dividing by a really small number gives you a really big number. All right. Okay, so it looks something like this. Okay, and that would be the graph of secant. All right, so it's the orange graph. Remember, the black graph was just there as a reference point. Okay, so again, and these can be shifted and transformed and so forth, just like sine and cosine, but that's not something we're going to ask you to do. We more or less just wanted to present to you what these graphs look like, so that way you're aware of them. So there's your reciprocal graphs as well as tangent.